In this video, we'll talk about the principles of energy through roller coaster problems, and we'll specifically examine how mechanical energies interact, which would ultimately help you understand how to solve trickier roller coaster problems. Now, roller coaster problems are a very great way to visualize gravitational potential energy and kinetic energy, and teachers love to use roller coaster problems to test students' understanding on the law of conservation of energy. Now, before we jump into the problems, I need to reiterate that the law of conservation states that energy cannot be created or destroyed, only transferred from one form to another. And looking at gravitational potential energy, how that formula Eg equals mgh comes from, it comes from the work formula, which states that the work done by an object is equal to the force applied times the distance it moves, or the displacement, times the angle of that force to that displacement. So in terms of roller coaster problems, this angle is usually just going to be 0, so the entire thing will equal to 1. So we get W now is equal to F delta D. Then we know that the force applied in terms of gravitational potential energy would be mg. It's the mass times the acceleration due to gravity. So we can sub that in, and displacement, or the change in distance, is in this case just the height, change in height. And because we know by the work energy theorem that the delta E stands for energy is equal to the work, we know finally we come to that conclusion that Eg is equal to mgh. Now for kinetic energy, we start with the same thing. We start with the work formula. Then we know that F, the applied force, is equal to ma, the mass times the acceleration. And similar to the gravitational potential energy, this would be, the angle would be 0. So this entire thing would just equal 1. Now, going back to kinematics, we have one of our big 5 equations, which is V final squared is equal to V initial squared plus 2AD. And rearranging that, we get delta D is equal to V2 squared minus V initial squared over 2A. A being the acceleration, V2 or V final being the final velocity or speed, and V1 being the initial velocity or speed. Then we can sub this rearranged equation back into our equation here. And we know, similar to the gravitational potential energy, that our delta E, or change in energy, is equal to work. So what we get here is that our kinetic energy, or change in kinetic energy, is equal to half times the mass times our change in speed. Now, usually in roller coaster problems, we might start at the top where it starts from rest. So the initial speed would be 0. So what we get are the typical kinetic energy formula. Now, some of you may have noticed that I exclude friction. This is because in an ideal roller coaster, the track would be frictionless. However, if we do take into account friction, because there will be problems that I'll also show that includes friction, then our equation, which is that we know that our initial energy is equal to the total final energies, and because they're all mechanical energies, meaning that it's just gravitational potential energy and kinetic energy in this case. So we know that the initial gravitational potential energy plus the initial kinetic energy would be equal to the final gravitational potential energy plus the final kinetic energy. And including friction, now I wrote it as the thermal, meaning the thermal energy, because if you think about it, when you're rubbing your hands together, if you're creating friction, it generates heat. So when a roller coaster is going in its tracks through friction, that generates heat. So we can, in other words, we can say that the work done by friction is equal to the thermal energy. Now, one thing to note is that friction is a non-conservative force, meaning that it doesn't matter about where it started or where it ended. It matters about the path it takes, right? Because if it's like, if you have a roller coaster that's going in loops, right? If you just calculate the friction here and minus friction here, that wouldn't be everything, because you need to take into account the path it takes. Okay, so for the friction formula, what it looks like, or work of the friction, it looks something like this. Okay, so we know that back to our work formula, we have our W is equal to force, in this case friction, on delta D, and then our cosine. Now, for this cosine theta, we know that friction is always opposing the motion. In that case, if it's opposing the motion in the other direction, we know it's 180 degrees. So this makes our equation into minus delta D, because cosine 180 is equal to -1. Next, after we know this, we know that we know by the work energy theorem that our total energy would be equal to work, or change in energy, right? In this case, this energy would be thermal energy, because that's the only one we're calculating in the system. But we know that energy cannot be destroyed, so that loss of mechanical energy through that friction, or thermal energy, results in the magnitude of our work done by friction. So now we can plug this in here. So what we're left with is, now one thing to note is that energy is a scalar quantity. So since we are simply expressing how much work can be done in this case, which does not require any kind of direction. Now back to roller coaster problems, okay? Let's say we have a hill and a base. At this point, if this is a mass, an object, at this point they would experience the greatest amount of gravitational potential energy. And at this point, they experience the most kinetic energy. Now if you have trouble understanding this, think of it like this. If I say two markers of the same mass, but one is higher than the other. If I were to drop both of these markers, this marker up here, the higher one, the blue one, has greater potential energy, meaning that if I were to drop them, this would have greater potential to do work. In other words, if I drop these two markers at the same time, this object would experience more speed, meaning that it would hit the ground with more force. So, up here, we know that if we're only looking at the mechanical energies in this scenario, this would be its maximum gravitational potential energy if it's at rest. And at the bottom, all of that gravitational potential energy will be converted into kinetic energy, which is shown by that formula. But now let's hop into some simple roller coaster problems. So let's start with this simpler kind of roller coaster problem before jumping into the more trickier kind of problems that involve friction. So in this case, our roller coaster starts from 45 meters above the ground, and its mass is 20 kilograms, and the question is asking us to find the speed at B, which is at the bottom, and of course neglecting friction. So from our law of conservation of energy, we know that the total energy, or in this case we can write mechanical energy, initially would be equal to the final mechanical energies. It's from our law of conservation of energy. Now mechanical energy can be split between potential and gravitational potential and also kinetic energies. So we have our gravitational potential energy initial plus right, and now we can plug in the formulas. Right. So now we know that at the top of the roller coaster, it's experiencing no speed. Therefore, we can just simply say that we can just cancel this out because there's no speed. So this entire thing's zero, the initial kinetic energies. Then once it reaches B, there's no more gravitational potential energy if B is our reference height. So in that case, since B is our reference height, we can just go ahead and cancel out the final gravitational potential energy because the height would be zero. So what we're left with is mgh initial. And in this case, both sides have mass, we can go ahead and cancel it out. And rearranging for V final, which is the speed, we get some, that's what we get. Now we can plug in some numbers. So for our final answer, is square root of 2 times the acceleration due to gravity, which is 9.8, and our height, the initial height, which is 45 meters. Now you can go ahead and plug that into your calculator, and what you get is 29.7. Now rounding to 2 sig figs, because in this question we have 2 sig figs and 2 sig figs. So our final answer, let's write it over here. So that's our final answer. Our final answer is 30 meters per second. That's our speed at B. Okay, now here's a different problem. It's slightly harder than the one before, but we're still going to neglect friction. So we have a mass, a carriage, that's 50 kilograms. It's 25 meters above the ground. And what we're looking for is to find the speed at B. Oh yeah, by the way, it starts with the initial velocity of 2.2 meters per second. And then the second part of the question is find the maximum height at C, and in 3 significant figures. So in terms of our finding speed at B, let's write this over here. Question find speed. We know by our law of conservation of energy that all of our initial mechanical energies is equal to all of our final mechanical energies. Then breaking this up, we get mgh, summing formula, plus 1 over 2 m initial squared equals to mgh final plus 1 over 2 final squared. And now before I proceed, we know we can cancel all of our m's, our mass in this case. And we can, before moving on, I'd like to point something out. Okay, so we know that this is 8 meters. B is 8 meters above the ground. So a good strategy we can use is to set B as our reference point. So I'll just write a note over here. Let's be the reference height. Okay, so we're gonna let B be the reference height. Okay, now, in that case, that B is the reference height. That means that at B we can consider as 0 gravitational potential energy. So that's final. Makes simple. Now we want to isolate for Vf squared. So we get V final is equal to our square root of 2 times I plus 1 over 2 initial square. That's what we get. Now we're going to plug our values inside, so we know that CR 2 times 8 times our initial height, which is 25 minus 8. Wait, be careful right here. This is 25 minus 8 because remember we set B as a reference height, so our starting initial height is not 25 anymore. It's 25 minus 8, and plus 1 over 2. The initial is 2.2 squared. And that's what we have. Now, when we plug this in our calculator, we're going to get a speed of 18.39. And so our final answer for part 1 would be, rounded to 2 sig figs, 18 meters per second. I think I should. V final is equal to, I could say the speed at V is equal to 18 meters per second. And now we're moving on to part 2. So for part 2, we need more space. So I'm going to erase this. So for part 2, it says find the maximum height at C. So once again, let's mark this as part 2. Once again, we can set up our law of energy conservation. So it's E mechanical initial equal E mechanical final. Then we can sub in our formulas for potential energy. Right. Let's first okay, now subbing in those formulas, we get mgh initial plus 1 over 2 mv initial squared is equal to mgh final plus 1 over 2 mv final squared. Okay. Now we know the final. We want to find the maximum height. So if you think about when you're going on a roller coaster, it would be a little dangerous, but if you were going on a roller coaster and your roller coaster going as high as possible, at that top peak height, you're going to experience 0 kinetic energy, right? Because all of it would be converted to gravitational potential energy. So we just cancel our final kinetic energies out. Then we can isolate for our final height at C, which we're given as mgh plus 1 over 2 mv initial squared all over, let's see, g. Okay, now we're going to plug in the values inside. I'm going to bring this over here. So our hf is equal to 9.8 times, let's see. Oh yeah, by the way, all the masses would cancel out here, right? And then after we have the initial height as 25 And so let's see, that's 1 over 2. 2.2 squared. This is all over 9.8. Okay, so that's what we're gonna have with all of our values subbed in. Then we're asked for 3 significant figures. So when I put this in the calculator, I got 25.25 approximately. So when we round this to 3 significant figures, we're gonna get 25 points. In this case, well, actually I got like 24 point dot 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 dot. So this would round to about 25.2. Yeah, 25.2 meters. So our final height is equal to 25.2 meters. Now before we say this is our final solution, let's just double check. Does this make sense? We start at 25 meters, we go through all these loop-de-loops, and we go all the way up to C. Our initial speed is 2.2 meters per second. It's not that fast. So it does make sense that there's not much of a height difference, and it makes sense that we got a higher value compared to 25 meters because there's more kinetic energy at the start. So when you add all the energies together, there should be more at point C in terms of gravitational potential energy. So for this question, everything seems correct. Now we're going to move on to a more difficult problem that includes friction. Okay, so finally this problem, I added a little bit of friction. So as you can see, we have a 28 kilogram mass or roller coaster. It's sliding down from 55 meters, and then it goes up, and we experience some friction here. Our coefficient of kinetic friction is 0.3, just from B to C, for 80 meters and 22 meters. That's the height for final. So we can set this as our reference height, like in the previous question. And we know that the initial mechanical energies is equal to the final mechanical energies. Actually, let's do total because we're adding friction, right? So total. And what we're gonna get from that, right, plug in our formula, we know that we have our EGI plus EKI, well, that would equal to our EG final plus EK final plus our thermal energy, right? That's something special to be a friction. We can set our formulas, but before that, we know at the start, top, no kinetic energy. And since we set this as reference height, we can technically say that at our final motion, we're gonna have, at our final destination, we're gonna have no gravitational potential energy. So we can simplify this. We get mgh for initial height. That would equal to our formula for kinetic energy squared, then plus our thermal, which is also thermal energy, as we know, I think I derived before, is the work of friction. Now we'll carry this over here, and what we're going to get from that, if we take our mass first of all, wait, before we take our mass, remember work done by friction is equal to the magnitude, so, or the thermal energy is equal to the magnitude of the work done by friction. So the work done by friction, remember, is the kinetic coefficient plus our mg and our displacement. And now plug everything in, we can take our masses. So we're left if you rearrange it, you get the final velocity is equal to the square root of 2 times ghi, and then minus our work done by friction, which is, let's see here, oh, we don't need that. Okay, now, now what we get from this, we plug in our numbers. We're getting 2 times 9.8 times, remember, this is 55 minus 22, because that's our reference height. Then, let's write this more. Minus our 0.3, 9.8 times our final displacement, which is 80. All that under the square root, and we're left with an answer of 13.3. Considering sig figs, let's just say this was 2 sig figs, and let's say this is 2 sig figs, and our answer is 13 meters per second in terms of speed at C. Now before ending, I'd like to give you some tips and tricks, okay? So I have 4 listed here, and the first is to draw a diagram. Because sketching a diagram for the roller coaster can help you visualize where the energy is high, and then when it's low, that'll help you solve it easier. And also remember to keep the energy conservation in mind, because Energy is not lost. It just changes from potential, kinetic, and possibly maybe thermal. And remember to keep units consistent. Now, I see this a lot that students, they make a lot of mistakes because they may have not converted kilometers per hour or kilometers to meters, and in their formula, they have different kind of units. That's not good. Remember to keep all units consistent. Now, a strategy I can tell you is you probably want to write all of your units out in your intermediate steps. That will help you keep track of those units. And finally, practice. Man, I can't emphasize how much this is important. You gotta practice all these problems at various heights and also speeds to get more comfortable with these concepts. And I hope this video has helped clarify those tricky roller coaster problems. And if you have any questions or need any clarifications, you can always drop a comment below. And I'd like to thank you all for watching.